לא שומעים.
Okay. So I'm going to be speaking in English. I heard that it takes coffee 25 minutes to kick in. So I hope you all had your coffee after lunch. And the highlight of this presentation is going to happen in 25 minutes. And that's when the coffee is going to kick in. I already had my coffee and I'm buzzing now. So we should start this presentation about how machine learning can help us solve unit testing problems. So I'm up here, a bit about me on the slide over here. My name is Eli. And if you notice, there's an old computer at the bottom. Anybody recognize this computer? Pick your hand up. Wow, excellent. Commodore 64. That was my bar mitzvah present. It wasn't my first computer. My first computer was a Sinclair Spectrum 48K. There was a 16K, and we got the 48K. I was really happy. My father gave it to us, and he had a program. It counted to 10. And I was on the floor. I was amazed. And I tried to make it count to 20. That didn't work very well. But I got the Commodore 64 for my bar mitzvah. And I completely dissected it. I tried to make a joystick out of an old calculator, and it ended up like on the table in pieces. I managed to put it back together again, but then I understood that I'm better stick with the software and forget about the hardware. And that's where my legacy started. So, we're in a new age now. We're not in the Commodore 64 age, and there's lots of buzzwords running around now. We have DevOps, and we have Agile, and we have new methodologies, and we have the QA sitting together with the developers. I mean, that's crazy. 10 years ago, you told me this, I would say, no way, but they're sitting together, and it's a new world. They're always really happy in the year, and then comes along legacy code, and just spoils all the fun for us. You know, we just can't do it anymore. Okay? So, what's the thing about legacy code? Why is it even important for us, legacy code? Okay, so basically, your legacy code, I'm going to tell you a story. I'm going to go back, I'm kind of a dinosaur, to the first browser wars in the 90s. And it was Internet Explorer war fighting Netscape, the Netscape browser. And it was a great war because we as customers really enjoyed it. We had sites that had best view with Internet Explorer and sites best view with Netscape. And they were adding features like hell. It was crazy. You know, each company was adding new features really fast. And then suddenly, you know, it stopped. What happened there? And this, you know, I don't really know if this is what I heard, is that the developers at Netscape told the guys in the management, listen, we can't add features fast enough. Microsoft are adding features really quickly, and we can't do it. Let's rewrite the code. Let's rewrite the code, make it modular, make it easy for us to add features, and then we'll win this war. And the management said, go for it, yes, because they saw whatever, the budget for adding features and the budget for rewriting it, and it looked like it's worth doing it. And basically, legacy code was the reason that Netscape couldn't survive. It took them a year plus to do it, and by the time they did it, Microsoft already ruled the market. You know this project now, it's called Firefox, okay? All the Firefox browsers is what came out of this thing. So your legacy code basically has all your IP, and it seems that it's really nice to go and fix it, but it's really, really difficult to go and do it. Okay, I'll give you some interesting facts about legacy code, even though lots of people here, lots of developers and lots of teams don't like to touch it. But we all know that about 30% of the development is new code. This is the part that every team wants to do, and I'll talk a bit about that later. And 70% is maintenance. Okay, 70% of the budget goes to maintenance, and I think it's actually more. I think it's about 80%. So let's stick with the 70%. But the interesting thing about it is that out of that 70%, 45% is adding new features. Okay, so actually, we're adding more value in our legacy code than we're doing our greenfield new code projects. But everybody wants to write these new greenfield projects. The value is not good. The value is actually in the legacy code. So why don't we want to change the legacy code? We talked about it, we heard a presentation about it before. I'm going to just give a highlight of why it's hard to touch legacy code. The first reason is regression. Okay? Every time you touch a legacy code, you have to do a lot of testing in order to make sure that nothing fails there, because there is an uncertainty there. So I'll give you an example. Let's say you develop for 1 month, you need to QA for 1 month. When you develop for another month, you need to QA for 2 months. So you have double the features. And then if you develop for another month, you have to QA for 3 months, because there's triple the features than the first time. So every time you add a feature, the time to check it grows. And it grows exponentially. So this is a real big problem with legacy code, is the regression. Custom rewriting. We talked a bit about Netscape. And Netscape, their manager said, yes, rewrite it, because what happened was the developers came to them, and it happens in many companies. And they said, listen, it's going to take us 2 months to rewrite this piece of code and 2 months to add the 2 features. Let's just rewrite the whole code. And basically, it's going to take much more than what you thought. It normally takes 3 times as much as what the developer says. And that doesn't go into account because you go into the unknown here when you're writing new code. And it's very, very costly to actually rewrite this information, this data, these algorithms. And not only that, you have lots of hidden gems inside your IP that nobody wrote about it. You know, some bug from a customer came and some developer fixed it, and it's there in the algorithm, and that's your IP, that's your knowledge. And now nobody's going to rethink about how to, what it's supposed to do when you write a new piece of code. So you have to relearn all this from the beginning. So rewriting is more expensive than what you think. Developers. Okay. Developers hate legacy code. And that causes a lot of problems. It causes problems with the management, because they're trying to get the developers to do something they don't really want to do. And it causes problems with developers because they don't want to do it. Now, why don't they want to do it? Now, I think the number one reason, I call it the beer reason. Okay? When a developer wrote a new piece of code, he can go with his friends, with his pals to the pub, and take a pint of beer and say, you know what I did this month? I wrote this whole new Bitcoin system. I'm great. Right? And the developer next to him, he added more features in the legacy code of some bank, but he can't just sit and say, I fixed this new thing in the old the system of the bank, and it was really great. It's hard to talk about it. So there's not a lot of pride for the developers to touch legacy code, and this is the big problem because developers don't want to do it. It leads to rewriting the code, that makes the code really legacy because you have the same pieces of code written many times, but the developer wants to write it from the beginning. And that goes to the fourth thing, is unmaintainable. You have legacy code, very hard to maintain. You don't really know what's happening, you have to check it all the time. Developers don't want to touch it, it becomes a burden. So your IP, the thing that made your company great, in that software, instead of pushing you forward, is actually a burden for you. And it means that you'll see your business counterparts writing code much faster and spitting out features, and you'll feel stuck, because your legacy code is actually a burden. And how can we fix it? How can we make our IP, instead of being a burden for us, help us go forward, and with all the knowledge we have, help us get more customers? Okay, so I'm going to go back to a story that happened in 2008. It was the financial crisis in the United States. And I had a customer who was sitting just in front of the Lehman Brothers. It was about a week after the Lehman Brothers crashed. And the whole place was hysteric. I was surprised that they even invited me to come see them. I thought they canceled it. And from the windows, I was looking down, I think it was the 5th Avenue, and there were television vans on the road, and people going out of the Lehman Brothers with their boxes. In America, they leave the company with a box, and they were crossing the road to the other companies. That was the flow of things happening. And the government there were really surprised by this, and they put up a new law that you're not allowed to bet against banks crashing. Okay, so everybody has to change all their systems, all the automatic systems that are now not allowed. It's illegal to bet on failing banks, and the whole place was hysteria. So we had 2,000 developers and 2,000 QAs running around trying to do this little fix over the weekend. I was there about Thursday, and they had to finish it by Monday morning. Okay, so it was hysterical. You can imagine what it was like that. Except for the team I went to see, and they were sitting in the hallway on the couches, their foot up, just talking on the cell phone. And I said, what's happening? What's? They said, we have no bugs. We had no bugs. The QA checked our system. That's it. We finished already. We've implemented it. How did they do that? Well, they did it because they started by writing unit tests. They continued writing unit tests, even though there's pressure from the management to go and get that feature out because some customer is waiting for it. And they continued to make sure all the tests are green at all times. It was a religion for them. And because of this, they managed to fix something within the legacy code in a matter of hours instead of working for days and nightless nights. So if this is the only thing you can get from this presentation, this is what you should do. Start writing unit tests. Don't ever, under any pressure, let your guard down. Don't let anybody say, the manager say you have to release now. Forget about the unit test because that's when legacy code starts. And make sure that it's always green. This is, if you get this out of the presentation, I'm a happy person. So, having unit tests means you don't have legacy code. This is also written by Michael Feathers. What is legacy code? Any code without unit tests? If you live the life with unit tests, you'll understand this, that it actually works. When you have unit tests, you can change your code. It's very easy to change your code. You have the confidence to do it. It's not called legacy code anymore. Okay, so having unit tests means that you don't have legacy code. So if you want to kill the legacy code, you have to have unit tests. Okay, but most code in the world is not covered by unit tests. And you're going to go to a company and you're going to see that because of some kind of pressure or something happened, you have no unit tests. Okay, and the developers don't want to write unit tests. They don't feel like something they can tell their friends at the bar. I wrote covered my code with 20% unit tests this week. It doesn't feel right. Okay, so it's not really happening. Okay? Even though it's supposed to happen and it's a good way to do it, it's really hard to do it. And today we have the technology to allow the computer to write these unit tests for you. And I'm going to go a bit into what kind of technology you need in order to get to this kind of solution. So the first thing I want to say, I'm going to drink a bit, is that covering your legacy code with unit tests is not the same as PDD, as writing the test from the beginning. Because, and somebody said this before, it's legacy code. It has been run already in live, in production. It probably works. Okay, so you don't have to think about does it work or does it not work. You just have to cover the test to make sure that it continues working. Okay, this is something that is a big advantage for computer-aided generation because the computer doesn't really need to understand what the code does. It just needs to really understand how it does it. So it doesn't need to know the business logic behind it. It just needs to know what's happening really in the test and how to create the right inputs for it. That's one big advantage for it. I'm going to show you a very fast video of something that can actually happen. This is actually a real code that can be covered by unit tests. It's a simple method that does something special on a leap year, which is something that's really hard to test because you have to test the 29th of February. It happens once every 4 or 8 years, depending on what year you are. And if you want to test it, the QA would have a lot of problem testing it, and unit test is really perfect to test this kind of thing. And you can either write this manually, or you can just click a button. No. Wrong one. Okay, we just click a button, and it says suggest unit test, and it will just think about it and automatically create 2 unit tests. And you can run it, and the unit test has mocks inside it, and have a cert inside it, and has setup, ready to act a cert, and we have 100% coverage. And it's really just a small glimpse of what software nowadays can do to create the unit tests. Okay, so how can this amazing magical thing happen? What do you need in order to make a machine or a computer do that dirty work of writing unit tests that nobody really wants to do. Okay, so there are a few things that we need to understand in order to make this happen. The first thing is an isolation framework. Okay, isolation framework is like a mocking framework, but much stronger. It's a mocking framework that you don't need to create your code for testability. It doesn't need to be testable in order to test it. It makes your code testable in any case because it can fake anything in the system. Okay, so an isolation system is a system that takes your spaghetti code and allows you to isolate from that the actual code that you want to test. So it will fake databases out, and it can fake network devices out, and it can fake web services out. And it can fake static metadata. It can actually fake anything that is not important for the test. It can fake it out. In the example that we saw beforehand, this isolation framework faked out date time now, current date time, which is something that's in the system, and we don't want to change the date and then run the test because that will create a really bad system for us. It used to do it in the past, and then the email stopped running because the date was in the past, the date was in the future, and someone can get emails and the server got all messed up. We don't really want to do that. But we can use an isolation framework in order to isolate your code. So if we have an isolation framework, that's the first step to enable us to write these machine-created unit tests. The second thing is analysis, deep analysis. Okay? We don't have to understand what the business is behind it, but we do have to try to understand what is actually happening in the code. So which method is calling which method? Which data is being read in which places? Which data is being written in which places? Right? And if we map all this out, and then we can take a method or a group of methods, we can know how that affects the system. Okay? Is it writing data? Is it reading data? Is it calling other stuff that's reading data and writing data? And if you get all this together, you can start building a model for what the code actually does, how it's being affected. Okay, so we have the isolation, which allows to isolate parts of the code, and we have deep analysis to try to understand how each method affects another method. Okay, the third part is coverage. In order to know what we're testing, we need to run the code and to see what parts of the code we actually touch. So if we have an if statement, we need to get to an else statement. If we have an if statement without an else statement, we still need to create a test that the if statement is false, and we just jump to the end of that block. So we need to have some kind of coverage to understand what is actually being run in the code. And we have the machine learning. When we have those three things together, then we can set up the machine learning. Okay, the machine learning, basically what it does is it takes the code that we want to test, the method we want to test, and now it tries to set up all the arrange part, the act is easy, and it tries to do the assert part. And it's not really easy because we need to know what objects we need to create, we need to know what values we need to set up in order that we get to different permutations and different tests. If we just let the computer do it in one go, it becomes the space is exponential. You have three arguments of integer. Each integer can be whatever million different values. You understand how big the space is if you want to test every single value. So we analyze together with understanding how to build it, and we're able to build these parts of the code. So the machine learning tries to learn your code as you run it to try to understand what needs to be created, what affects the code, what doesn't affect the code. And at the end, what needs to be isolated, what are the effects outside of the realm that we are doing. That's the powerful mocking system. And what we need to assert, which is also difficult to know, because we can have a method that does many different changes, many different things in the system. We need to try to figure out what part of the system is important. Okay, so the system runs this method in different permutations. It learns how the system behaves, and from that it manages to create tests which are human readable, which are something that the developer can afterwards change it himself. And if it fails, it's easy to track back and to see exactly what the scenario was that it failed. Okay. Another part of the code, which is important, is duplicate tests. Duplicate tests are stuff discussed that because when we analyze the code and create tests, we can create the same test many times. Okay, so we have another part of the machine learning to try to understand what tests we already have the same scenario for, and we're not going to run them again. So even if we have the legacy code with 20% of it covered, and we run this through this machine learning system, we won't get duplicate tests. Duplicate tests are bad because then we have 2 tests failing for every failure, and that will just put noise into the system. Something's going on. Isn't that boring? Okay. So basically, I've actually summed up most of the presentation. Okay. This is basically what you need to do to create tests on your legacy code. Legacy code is important. It's more important than what you think it is. You have to keep it. You have to pamper it. Don't fall into the Netscape kind of let's rewrite it, because that never works. All these big bang rewrites always tend to fail. I'll get to later. And what we need to do we need 4 different features in order to create this code. When we understand that the code actually runs okay, so we're just laminating it, laminating the code. And so we need a great isolation framework, coverage, trying to understand the analysis of the system, and to use the machine learning to actually write the code. Okay. And I have a prediction. My vision is if you hear that machine software is going to test the software that you software developers wrote. That's my vision, and we're getting there and it's getting close. And my prediction is, if you remember the slide at the beginning where we saw that 45% of that 70% was actually writing, adding features into legacy code, my prediction is that percentage is going to grow higher. And I think about 60% of the new features are going to be added into legacy code instead of only 45 today. Do you have any questions? This is a great time to ask questions.
Why do you refer only to legacy code? You have to write unit tests only also for new code.
Of course you have to write test for unit code. That's the first thing I said that, with my example of the Lopian, that these guys, they wrote unit tests for the new code from the beginning. They kept writing it, and that's why when they had to create that feature, they managed to do it really quickly. The thing is that most of the code in the world is not covered by unit tests. And to try to jumpstart and to get to that position, it's going to be really hard to do it without having a tool that does it automatically. Sure, everybody should do TDD. TDD is great.
What makes the code become legacy, or when does it become legacy?
That's a nice question. When does the code become legacy? So if you go to Michael Feather's definition of legacy code is any code without unit tests. So the second you write a code without unit tests, it's legacy code. Okay, but you can always write that unit test afterwards. So basically, I like there are a few definitions. I like the definition we heard beforehand. It's code that you're scared to touch. So it could be many reasons. You know, the developer left. Something happened and the old code suddenly surfaced, which wasn't once legacy code. All these different things can happen. But once you don't have the confidence to change the code, that's when you call it legacy code. And another nice definition that I heard is that if you as a developer don't want to touch it, that's legacy code. Because developers, when they get to legacy code, they're like, they'd rather massage the marketing team than to touch legacy code. And if developers hate anything more than the QA, it's the marketing team. So just understand how much this legacy code is a burden. Okay. So thank you very much, everybody.